And I'll be like, let's go right now. And me, my son, we can take it. Right, but then I'm like, we don't like so much kind of extra. So, I always get here trying to like walk. It's like,
She's like, oh, you know.
you'll still be on the
No, I know about it. You don't even know the word. When she told me so we needed it.
I don't.
Why would she say we just have to go to that?
Yeah, I did a one order. Today, I really saw a lot.
Yes, it was so good. I saw it practicing.
All right, guys, page 48. This is our final topic. If we get through with this, then we can start our quiz review packet. The quiz review packet is for you to keep. You can write in that one. All right, so optimization. Optimization is the process of finding the greatest or the maximum optimal solution, or least value, the minimal optimal solution, which must be true regardless of the solution. Optimization finds the most suitable value for the function when given within the given domain. Now, we don't have to worry about whether something is maximum or minimum. Really, you're just finding the critical point. So basically, you're just going to set the derivative equal to 0. Okay. That's all you need to do. You don't have to worry about, wait, is this going to give me a maximum or a minimal? Whatever they're asking for, the critical point is going to get you to, so you don't have to worry about, one versus the other. We just have to set the derivative equal to 0. That's really half the battle. What's challenging is sometimes the equations, there's multiple equations, and we have to get the equation that we're trying to find the derivative for down to one variable. So we have to do, we have to first create the equations, and then we have to substitute one for the other. But then after that, it's just power rule, set the derivative equal to 0, and solve for x. And once you solve for your missing variable, then you're just rereading the problem and providing whatever variable that they're asking for. So the big picture is, if I can just get my equation that I want to find the derivative for, down to one variable, set the derivative equal to 0, and you're basically at near the end. Okay, so we're going to have to write the equation for the variable that you want to optimize, and there's going to be context clues in the problem that tells you which variable they want you to use, and then you're going to substitute to get the equation in terms of one variable, and then you're going to just simply set the derivative equal to 0 and solve. All right, so let's look at number 1 here. A manufacturer wants to design an open box having a square base and a surface area of 108 square inches. What dimensions will produce a box with maximum volume? So there's the key word there. Anytime we're looking for maximum or minimum or optimal of anything, it's always going to describe what you're trying to find the derivative for. So we're trying to optimize volume. Now, we're going to have to be able to know these formulas. I know that with related rates, I gave you all the formulas, but really the formula that you have to be able to know is just for volume of a rectangular box and surface area of a rectangular box. And I'll go through the steps for that. So volume put a star next to that because this is ultimately what you're trying to optimize. You're trying to get this volume equation down to one variable. What's the volume formula for a rectangular box? Yeah, length times width times height, right? So that's not too bad. We should know that. So x times h. They tell us that it's a square base. So if it's a square base, we know these two have to be the same, but they don't say anything about the height. So we have to produce a different variable because they're not linking that connection between the base and the height. So we're just going to say x squared times h. There's also a mention of surface area. We're going to have to know how to build the surface area of a box. Now, I don't want us to think of this as a formula to memorize because every dimension is going to be a little different. I just want us to think about those two words there, surface area. All you're doing is you're just adding up the area of each of the surfaces. And each surface is just either a rectangle or a square. Okay. Now, how many sides do we have? It's just 5. Okay, so there's only going to be material on 5 sides of this box. Okay, so let's just go down and go through and just find the area of each of the boxes, or sorry, each of the sides. Start with the base here. What's the area of the base? X squared. Okay, so that's one surface area. We have 5 more to go. What's the one facing us? This one that's facing us here. What's the area of this box? X times h. Okay. How many of this area do we have?
4.
4. But first, let's just say this one and the one behind it, right? So that one, this one and the one behind it. So I want to list out all the ones so that later on, if you want to combine them to speed up, you can. So I have the front facing and the back facing. So that's xh and xh. And then the ones on the side is also x times h. And then the other side is also x times h. So we have 5 sides, 5 surfaces that we're accounting for. We have a square, rectangle, 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 rectangle. 5 surfaces. We can combine like terms there. So x squared plus what? 4xh. Okay. So this is the way that I want you to find the surface areas. Sometimes the base may not be squares, and if that's the case, then just identify whatever variable that is, and but ultimately it's either 5 or 6, depending on if it's an open or a closed box. If it's a closed box, then there's going to be 6 surfaces that we have to account for. If it's open box, then it's just 5 surfaces. All right, any questions there? All right. Let's see. They do give us information about surface area. So surface area is 108 square inches. So we can go ahead and put that in for S. So these are the 2 equations we're working with. Okay. We're trying to find a way to get this equation to be plugged into this equation, but we would like to get the volume equation down to one variable because this is what we're trying to find the derivative for. Now, which variable would be easier to replace to solve for? H, yeah. So we're going to focus on the variable that is easier, that has less restrictions. The x squared may be harder to solve for. So we're going to solve for h. And if we solve for h, we can find a replacement for h. So here, we're going to find a way to get that h to be replaced so that we can get our volume equation down to one variable. So we're going to work with this equation to try to solve for h. So there's our goal here. We're trying to solve for h for 1 so that I can replace it into the equation that we're trying to find the derivative for. So I move that x squared over to the other side. I want to get h by itself. So what else can I do? Divide by 4x. So 108 minus x squared over 4x is equal to h. So there is my replacement for the h inside the volume equation. And again, we know that we're doing this. We're focusing on this formula because that's the formula that we're ultimately trying to get ready for our derivative. So v is equal to x squared times 108 minus x squared over 4x. Any questions so far? Right. The only rule you need is power rule. So if we get this cleaned up all the way, the only thing we need is power rule. There's no need for product or chain or quotient. We just have to spend time cleaning this up. Okay. So let's get it all cleaned up so that the only rule that we need is power rule. So I'm going to distribute that x squared through. I'm going to just continue working on this equation until the only thing I have left is having to use power rule. So I'm going to distribute that x squared through. We know that if we're dividing by a single term, that we can just flip into individual fractions. I continue cleaning up. 108 divided by 4, if I use my calculator, that comes out to be 27. X squared and x just becomes x. And here I can just pull this as a 1/4 in front of my as my coefficient. X fourths and x can cancel out. So I'm left with 1/4 x. So the formula that we're trying to ultimately get ready for power rule, we got it down to one variable. We got it all cleaned up so that the only thing we need is just power rule to find v prime. Okay, so now set v prime equal to 0, or find v prime first. Power rule. Set equal to 0, and solve for x. So really, you're just getting the variable or the formula that you're trying to work on down to one variable on the right side, get it cleaned up so that power rule is the only thing you need. Find the derivative, set equal to 0, and then solve for x. Dividing by 3/4, the same thing as multiplying by 4/3. I can multiply this out, or I can just see that the 27 and 3 can reduce to be 9. 9 times 4 is 36. So x is just equal to 6. We're not going to do -6 because -6 is not going to make sense for the fact that these are dimensions of a box. So x equals 6. And then once you have your x value, go back and reread the problem and see what they're asking for. Sometimes they're asking for that volume. Sometimes they're asking for height. Sometimes they're asking for the dimensions. In this case, they're asking for the dimensions. So we just have to provide the base, and the height. Okay. Once you have your x value, there's no need to create any more new content. You're just trying to find, everything should be ready for you to plug in. So how can we find the height? Yeah, either surface area, or you can plug it into an equation that's already designed for that h. So, but yeah, you can use any of variation of these equations, but I'm going to pick out the one that I find more efficient. So I'm going to just plug 6 back in for x to find the height, because we just are looking for our dimensions here. We have our base length. We're trying to find our height. Okay. So height is equal to 108 minus 6 squared over 4 times 6. I get height of 3, and we have our dimensions, right? Our dimensions is x and h. So 6 inches by 6 inches by 3 inches. So because we found the optimal value, we're able to take the surface area restriction and create a dimension that will maximize our volume. And that ultimately just comes from where the rate of change is equal to 0. Whenever the derivative is equal to 0, that's going to create the optimal solution that we're looking for.
That one sort of final answer should we, or can we write that x equals 6 and h?
Yeah, that's fine as well. It's asking for dimensions, so as long as you identify all the length, width, and height, but because length and width are the same, you can just say x is 6 inches, h is 3 inches. All right, page 49. All right, rancher has 200 feet of fencing with which to enclose 2 adjacent rectangular regions. What dimensions should be used so that the enclosed area will be a maximum? So the two formulas that we're working with are perimeter versus area. But which equation are we trying to optimize? Area. Okay, so you see the word maximum. Maximum is describing area. So ultimately, we're trying to get the area equation down to one variable. But first, what is the area of this region here? Length times width, right? So what's the length and width?
2x.
2x times y. So we're all, our goal is to try to get this down to one variable so that we can find the derivative, but we're going to need the perimeter to help us with that. So let's create the perimeter equation. So perimeter, I'm just going to just add up all the lengths that's identified here. So perimeter is also going to include the middle set of fencing here. So I have 2x here, and 3y's with vertical. So I'm going to say 4x plus 3y. So 2x is here, 2x is here, that's 4x. And I have 3 vertical y's, so plus 3y. Okay, what can I replace p with? 200. So now we're just trying to get the area down to one variable. Is there one variable that's easier to solve for perimeter? Okay, not really. So you can solve for either variable, it doesn't matter. If I have to choose, typically I like to get everything in terms of x, but it really doesn't matter. So I'm gonna just find a replacement for y so that my area equation can be down to x. But if you did it the other way, you would just find you would just solve for a different variable, but ultimately it's going to end up being the same process. So I'm going to, this is my preference. I'm going to solve for y, especially if they're virtually the same difficulty. Divide both sides by 3. So there's my substitution into my area. And I'm just trying to get my area down to one variable. So that's why I solve for one variable. So I in the other equation and replace. So here's my updated area equation. Right, so the key thing here is you only need power rule. So spend the time to clean everything up because I mean, you could go through product and chain and quotient, but there's no need. There's, if we just go through our cleanup step, our calculus can just be a lot easier to manage. So I'll distribute the 2x through. And as I do that, I'm also just separating into individual fractions. And I'm just going to rearrange so that my derivative feels a little bit easier here. Okay, find A prime. Power rule is all we need. Set equal to 0, and then solve for x. Cross multiply. Divide both sides by 48. I got x is 25. Okay. Again, it's asking for the dimensions, so all we need is x and y. So we have x, just plug into an equation that has a y already defined. So 25 in for x. Okay, so we have our dimensions here. X is 100 over 3, and y is 25 feet. All right, page 50. Okay, we're going to do area, volume, area and surface area again, area and perimeter again. But this time there's going to be a cost involved with this problem here. So we have a rectangular field fenced off along the bank of a river. So say we have 3 sides, and we have so we have a river on this side, so there's not going to be any fencing on this. It's just going to be on the 3 sides there. If the material for the fence costs $8 per running foot for the 2 ends and $12 for the side parallel to the river, find the dimensions for the field of largest possible area. So this is our goal here. We're trying to find area enclosed with $3,600 worth of fencing. So I'm just going to assign this to be X. It's a rectangular field, rectangular region. So I know that these can be the same. But if you did X here and Y, that's fine. I'm just going to do my horizontal as X and my vertical as Y. All right, so area. What's the area x times y, right? Length times width. Put a star next to this since this is ultimately our goal. We're trying to get that area down to one variable so that we can work with it. The perimeter is going to be the cost, okay? Because the cost is going to be associated with the actual fence that we're buying and that we're putting in place. So perimeter and cost can go together. Now, there's going to be a cost associated with each of the sides. So the side that is parallel is going to be more expensive. So this is going to be $12. And then the size that's the two ends is going to be cheaper material. So it's going to be $8 per feet. So perimeter slash cost, we're just going to associate multiply, however long this is, we're going to have to multiply by 12. So 12x plus 8y plus 8y. And that will give us, depending on the dimensions, we can factor in the cost because this is going to be cost per foot. So 8y plus 8y plus 12x. Okay, I'm going to update this and just call this the cost equation. All right, what do you know about the cost? What's in our budget here? 3,600. So let's go ahead and replace. This is how much we have to work with. So now we're trying to get this equation to get into this equation. Is there an easier variable to solve for? Okay, they're about the same, right? If I solve for y in terms of x or solve for x in terms of y, they're relatively the same. So if they're the same, I'm just going to find a way to get rid of the y or trying to solve for y. If you solve for x, it's the same difficulty. Okay, divide both sides by 16. All right, so here's my replacement. Plug it into the variable that I want to replace. And again, my goal is to try to get my area equation down to one variable. X times right, again, your equation looks complicated, but really all you need is power rule. So spend the time to distribute, split up into individual fractions, and the derivative should be relatively easy if we do all the cleanup we're supposed to do. I'm going to reduce here. So 3,600 divided by 16 is 25. Sorry, 225. And 12 over 16 can reduce to be 3/4. Again, you don't have to reduce. I just find it easier to find. If I can reduce along the way, then my equation will be easier to work with because I'm just dealing with smaller numbers. Okay, so find a prime set equal to 0, and we have our critical point. So a prime, power rule. Sorry, it's 3/4 x squared. I forgot to distribute that x through the second one. So 225x becomes 225, 3/4 x squared becomes 6/4 x. Once you find your derivative, you're always going to set equal to 0. And then you're just going to solve for x. Dividing by 1.5, the same thing as multiplying by 2/3. My x is 150 feet. It's asking for the dimensions here. So the y value, we can just put it into the y value that we've already created. So 3,600 minus 12 times 150 all over 16. Going to get us 112.5. All right, number 2. We have a rectangular storage container with an open top. The length of the base is twice its width, sorry. The length of the base is twice its width. Material for the base costs $10 per square meters. Material for the sides is $6 per square meters. Find the cost that will create the cheapest container. And the hint is we're trying to minimize the surface area. Let me draw the. So we do have a relationship between the bases here. The length of the base is twice its width. So we can call one side x and the other side 2x. Because we don't have anything about the heights, we have to give it a different variable, either use y or use h. I'll just use h here. The cost is going to be associated with the sides, but we'll do that a little bit later. Okay, we'll do that a little bit later. Volume. What's the volume going to be? Good. So length times width times height, I get 2x squared times h. We do have information about the volume, so we can go ahead and replace v with 10. Okay, we'll come back to this, but this is not what we're trying to optimize. Right? We're trying to optimize the cost, which is related to the surface area. So let's build the surface area first. Now again, we're just going. Now, how many sides are we? How many sides are we working on here? 5. Yeah, open top. So we'll just do one side at one area, one surface at a time. Let's start with the base. What's the area of the base? 2x squared. Okay, so that's 1. Let's do this side here, the front-facing one here. What's the area of this front face? XH. Okay. If there's an XH in front, there's also an XH in the back, right? So we know we're always going to get 2 sides that are with the same dimensions. All right. What about the longer one here? What's this longer side here? 2XH. Okay. If there's a 2XH on one side, there's also a 2XH on the other. Okay. So I just want us to be able to build it piece by piece. I don't want us to feel like we have to memorize, a formula. You're just going down, you know that there's 5 sides and you're just using your rectangular formula to find the area of each of your surfaces. Okay. Are we good so far? All right. Now, there is cost associated with each of the surfaces. The most expensive is the base. The base is going to be the most expensive material. So we're going to have to work in the $10 into the base. Okay, so we'll do that in a second. The sides cost $6 per square meters. So we just have to multiply this by 6. So each of the surfaces for the sides is a cheaper material than it is for the base. Okay, so now I'm going to update this and call this the cost equation because we have dollar amounts associated with the material. So we're just going to multiply this through. So this becomes 20x squared. If I add up all these sides here, what does that give me? 6xh, multiply that by 6. Yeah. Okay, we're trying to optimize the cost, so put a star next to this. We're trying to get that cost equation down to one variable. And we're going to use this volume equation information to help us out. Okay, which variable do we want to replace? Would be the easiest one to replace. The h, right? The h is by itself, so that's going to be a nice one to target. So we're going to solve for h, get this in terms of x, get our cost equation in terms of x, get it ready for power rule, find a critical point, and then we're going to be near the end of our problem. All right, but we do need this cost equation cleaned up down to one variable. So I'm going to solve for h. Reduce. Okay, if we bleed into this, I mean, if you're if you have your packets, we're not going to do number 3. So if you need the space for 3, we're going to use it. Again, the only equation, the only rule we need to get ready for derivative is just power rule. So let's just get this cleaned up so that all we need is power rule. So I'm going to continue working on my cost equation. Multiply that 36 through. 36 times 5 is 180. There's an x left in the denominator, but I'm going to bring it up to get it ready for power rule. Okay, your cost equation. This is what we want to ultimately find the derivative for. And we're able to get it all the way down to one variable and ready for power rule. So ready for C prime. (20x squared) becomes 40x minus 180x to the negative 2. Find your critical point. And then try to figure out how to solve for x. Cross multiply. This is not going to come out to be a nice integer value, so we'll just make the calculator give us a decimal value. Okay, 1.651 or 1.6509 meters. Let's see what they're asking for. There it says, find the cost of the material for the cheapest container. Now, whatever the problem is asking for, there's already going to be a formula already defined. So we shouldn't have to create any more new material or new equations, because everything that we need is going to be already be defined. So it's asking for the cost. So we just have to find a cost equation to plug into. We have multiple cost equations. Either one is fine. We'll plug the 1.65 in for X, and we'll get the cost. Okay, if they're asking for the H value, then we can find an equation that has an H already. So when you find your X, the only thing you need to do is to plug into one of the established equations that you've already created. You don't have to create any more new equations. Whatever they're asking for, you already have those equations built. So I'm going to plug that 1.65 in for X. Either of these can work. So cost of at this 1.65 meters will give me a dollar amount of 163. You're just plugging into the calculator. So either you plug that 1.65 into this cost equation or this cost equation. Just make sure you don't plug the C prime. That's something different, right? You just want to identify an equation for you to plug in. So just to let you know, there's only going to be one optimization problem on the quiz, and it'll be this type of problem. It'll be involving cost and surface area and volume. So all we need to really focus on is trying to get practice with this form of problem, and that's the only one I'm going to put on the quiz. Okay, a few minutes here. Let's see if we can get started with the review. So did everyone pick up review packet? If you get to, this is for you to have. Okay, let's review mean value theorem. So mean value theorem comes with two conditions. Our function needs to be established with a continuous statement, brackets. Our function has to be established with a differentiable statement with parentheses. And then the formula is this. You're going to find the slope between the endpoints. And then you're going to set that equal to the derivative. And then solve for that x value. Okay, we're trying to find whatever slope that lives between the two endpoints. We're trying to find where that slope is going to occur on the curve. All right, is this function going to have any trouble with the first two conditions? No, right? Polynomial is going to be safe. No issues with continuity, no issues with differentiability, but we do need to state those conditions as part of so we'll say y of x is continuous with bracket 1 to 3. Y of x is differentiable, parentheses 1 to 3. Okay, I purposely wrote the formula this way so that we're forced to do the slope first before the derivative. If you find the derivative first, you may end up starting plugging values into the wrong function. So force yourself to find order pair slope at the function level before you move into the derivative. So we'll find y of 1. You can use your calculator here if you like. Okay, using this information, you're going to create this is the average rate of change here. And that's just the slope between the two endpoints. -3 change in y over change in x. -8 over 2, which is -4. Okay, so now we know this is our average rate of change. This is the slope that lives between the two endpoints. And we're just now trying to ask the derivative to tell us where the slope is going to live on this curve. Okay, move into your derivative portion. So now you're just setting these equal to each other, right? You're asking the derivative to tell us the location where there's going to be a slope of -4 on the curve. Divide both sides by -4. X equals 2. So that's our C value. This is guaranteed. Is this safe between the two endpoints?
Yeah.
Yes. Okay, that's a guarantee. If you find a C value and there's only one C value and it lives outside the interval, something went wrong. We have to get at least one solution that lives. As soon as we get these two conditions to pass, we should be able to get this to be a guarantee. Okay, no homework tonight. I want to walk through this with you in class. So we'll have tomorrow all class period. We'll have Monday all class period, and then Tuesday is your quiz. Okay. Help session will be Monday morning. AB is also having a quiz on Tuesday, so they're going to have a help session Tuesday morning. I'm going to give you guys a help session Monday morning. Okay. Thank you. Are you? Thank you.